Okay, so let's see if we can tackle this first question because it's kind of a lot. So it says that a bag of road salt used to melt ice and snow from roads contains a mixture of calcium chloride and sodium chloride. Okay, so we've got a mixture between the two. A 2.765 gram sample of the mixture was analyzed by first converting all the calcium into calcium oxalate. Okay, then it was dissolved in H2SO4. The reason why it did that is so that we could put it in acidic conditions. So that's really the only reason why that's here. And then it was titrated with 0.1 molar KMNO4 solution. The titration required 24.65 milliliters of KMNO4 and produced Mn2 plus CO2 and H2O. So you were correct about what would be observed at the equivalence point. Now let's make the distinction. The equivalence point is where the moles of the titrant equals the moles of the analyte. Now the titrant is what is in that burette. That's the burette one. And the analyte is what is in your flask. Okay. That's the one you were analyzing. This is the one that you know of, the concentration that you know of. So let's think we actually in this case, the titrant would have been KMNO4, and then the analyte would have been the calcium oxalate. Right. So that's actually okay for now. I'll come back to this one. But that is what would be at the equivalence point. The equivalence point is when the moles equals moles. So now at the end point, that is the answer that you put. So that is when you would see an observational change. So make sure you understand that clear difference because I bet you they'll throw you that one. For this, you want to write the half equation for the oxidation reaction starting with C2O4 2 minus, and for the reduction one with MnO4 minus. So let's see if we could get an equation out of here. We've got a few things here. These are important. It seems that NaCl is not important. We're going to determine how much calcium is in there, how much calcium chloride is in there by converting the calcium into calcium oxalate. Then we will determine how much calcium oxalate there is by titrating. So let's just look at the titration one, which is going to be between these two right here. So essentially, the three things that I had there were my calcium oxalate, my KMNO4, KMN, there's not an MM, and we had that acid that was just to put it under acidic conditions, right? And it only gives us the information to say that we only produced Mn2 plus, we produced CO2, and that we produced water. Okay. Now, the sulfate right here, there's no sulfur on the right side. So this is obviously not an incorrect equation, but it gives us a good place to start. This hydrogen is making the water. And this KMNO4, there's no potassium over here. And there's no calcium over here. These are what we would call spectators. So we're going to cut those out. We don't really need them. We're going to, when we show our half equations. So let's see if we can write the equation without the spectators to make it a little more clear. So we're going to have oxalate, C2O4, with the 2 minus charge. We're going to have Mn. I did it again. I can't believe that. MnO4 with the minus charge. And let's just forget about that guy. And we're going to have Mn2 plus. We're going to have CO2. Let's go ahead and keep that water. Okay. Oh, okay, so let's just say we had that hydrogen there. We'll just keep the hydrogens. It's still not correct, but it simplifies it a little bit. Okay. So the way that I am thinking about this is I'm thinking, oh, okay, so the oxalate is coming from here to here, and then here, this is coming from here to here. All right. These are what we're talking about right here. And these are going to make up our half equations. These guys are just kind of ornamental, and they're there to balance the equation either by mass or by charge. So for 1b, it asks you to write the half equation for the oxidation reaction starting with C2O4. So I'm going to start with C2O4 2 minus, and my half equation is going to be CO2, 1 to CO2. And let's see if we can get 1C. I will show, let's see, MnO4 2 minus, and I'll take it to Mn2 plus. All right, so you will notice that these are not balanced. To get the correct answer, we'll have to balance them. So we will balance them the long way by adding, we have to add first balance by mass. So we're going to put a 2 here to balance that, to balance the carbons. And we actually balance the oxygens instead. So oxygens are great. So now we need to balance the charge. Well, that actually just means that we need to add 2 electrons here, and that ends up being totally balanced. We don't have to add any H pluses, we don't have to add any waters, we don't have to add anything else. That one's all good to go. All right, so for MnO4 2 minus, and then this one, we're going to have to actually add some I'm going to rewrite, and I'm going to add 4 waters on the right side so I can balance out my oxygens. And then so now I need to balance my hydrogens. So I have 8 hydrogens on the right, so I'm going to add 8 hydrogens on the left. Now hydrogen is added as a H plus. Okay. And I like to, when I explain this, I like to write it out in multiple steps. You don't have to do that. You can just add a term to the right and a term to the left. And just keep adding terms to the left and right if you want. Now when I do this, so the next one is I have 8 positive charges and then a 2 minus charge. So I end up with a 6 plus charge over on the left, and I have a 2 plus charge over on the right. So I need to take this 6 plus and turn it into a 2 plus. I need to balance the charge. So I'm actually going to add, let's see, 6. So I'm going to add 4 electrons right here. Okay. So once I do that, then I'm good. I'm adding 4 electrons here, which is going to be your reduction, right? Because it's the gaining of electrons. And then this is my oxidation because it's the loss of electrons right here. And notice that your electrons are on opposite sides. So that's super helpful. Now, you also notice that your electrons are not the same. So let's go ahead and fix that. We're going to put 2 C2O4 and then 4 CO2 plus 4 electrons right there. So then that way, whenever we put them all together for 1D, we want the overall equation for this redox reaction. We are going to put everything together that, let's see, and have 8 hydrogens, MnO4 2 minus, plus 2 C2O4 2 minus, makes Mn2 plus 4 CO2 plus 4 waters. I did not add them in any rhyme or reason. I just grabbed elements from the left side here, put them here, and I grabbed this and I put it here. I didn't add the electrons because the electrons cancel out. We have 4 electrons on the left, 4 electrons on the right, so they cancel out. So this Mn came here, the CO2 came here, and then this came here. All right. So that's the overall equation, and that's actually what you used in that titration lab. So that is it derived. Hopefully that clears up questions on question 1 and also the one on the back. All right.